Welcome back. We will have the first mini-course lecture of this week by Alexander Zhiboedov, and we'll talk about gravitational S-matrix scattering.
Thank you, Francesco. Thank you very much for the invitation and suggesting this amazing topic to talk about. So I will be speaking about gravitational scattering in asymptotically flat space-time. And I think there are many open questions in this subject. I hope you will improve much of what I say, maybe using the Bootstrap methods. And so that's why I think this is maybe something interesting to go back and see what's a physical picture. So my goal would be basically to present you a physical picture which appeared, as far as I can tell, conservative version of a physical picture that appeared in the last 40 years that people thought about the problem. And then to me it seems to be very interesting to improve it, to test it, to see if it makes sense, or maybe it does make sense. So let's see how far we get. But to motivate a little bit the subject, let me start by, if we talk about gravitational S-matrix, you can ask why are we, if it's ever relevant or interesting. Well, and recently, one, of course, obvious context where people did many computations and made a lot of progress is the physics of gravity waves, where you can use scattering amplitudes, and you can call gravitational S-matrix to learn some interesting things. But I will not be talking about that. I will be more of taking a particle physicist point of view. And then, of course, as you know, if you take real experiments at colliders, gravity is completely irrelevant. So what do we do about that? Well, there are a couple of things we can do. One thing, just let me mention, people discuss. If you have Planck constants and say small d number of dimensions, okay, it starts. Now I have to learn. So let's, okay, well. I will manage. So let's say we have a theory in d dimensions and we compactify it to little d dimensions. So then we can have a Planck scale in little d dimensions to the power d minus 2 equal to the Planck scale in a large d dimensions. And here you have the ratio of the Planck scale to the some kk scale of extra dimensions. And one way to make gravity important is to imagine that, in fact, the fundamental Planck scale is much lower than our d-dimensional. So this is a tiny number. Let's imagine that this number is much bigger. How could it be? Well, it could be if we have this large extra dimensions. And so in this way, the gravity can become important in some collider experiment. So this is something people discussed a lot in the past. But there is another way to make gravity important, and this is to consider large energies. So when we take high energies, then gravity becomes important, and this is because all the coupling constant change with energy, and gravitational coupling grows very fast, and it's really at high energies where we think the gravity will shine. So in this, from this point of view, the focus of these lectures will be, I will be just talking about gravitational scattering at high energies, and the reason being simply that, if you have a standard model or string theory at low energies, there are many non-universal features, but at high energies we believe that gravity takes over, and at least there are some things we can say universally. So second, so this would be the focus. Second, let me mention that, if we're talking about gravitational S-matrix, we assume that this, and I will do that, I will assume that this thing exists. This is not obvious for a couple of reasons. Well, one simple reason, I will assume that D is larger than 4, this number of space-time dimensions, and this is related to IR divergences, but I think many of the formulas, and I think, well, I hope some of the conclusions should be easily translatable to D equal 4, but this is an open question, what is the right framework to think about it in D equal 4. But more importantly is that I will assume that there is really, the set of observables is described by an S matrix. And as you know, that this is really not obvious. And some people in the past famously said that there is no S matrix for the process of black hole formation and evaporation. And the question is, okay, I think an interesting question in this regard is that since we do not have, we have some doubts if this object makes sense or to what extent it makes sense, it's really interesting to test it. And that's the spirit, of course, of this matrix bootstrap. We will assume that the things which we usually prove in quantum field theory, such as analyticity, crossing, and unitarity, that they hold, that this object exists, and we see is it consistent with gravity or not. That's a basic idea. Now, well, let me make a spoiler. As 2024, I think the answer to this question is yes, it seems consistent. To all the tests we did, it seems consistent on one hand. But on the other hand, it seems to me that not really black hole physics or some of these subtle properties has not been really used much. And so it seems to me that it's here that maybe one can make more stringent tests. Now, in fact, in the last few years, there have been a lot of progress in sort of studying this object, and gravity behaves as a normal EFT. If you have something heavy, you integrate it out at weak coupling, your Wilson coefficients are suppressed by the gap. There is not much, some miraculous violation of EFT we haven't observed. But why do we really, let me just say, why do, let's say this is my assumption that this object exists, what is this assumption based on? And, well, I guess we can say three things. One is it's an example of string theory, where it seems to make sense, and it makes sense in perturbation theory. Second, I would say it's flat space limit of ideas CFT. And finally, people recently have been revisiting various further conjectures within string theory where you can define the S, such as BFSS or matrix string theory, where you can define the certain matrix element as a limit in a space of theories. So you have a set of objects, and then you take this limit, and in the limit, where this n, say it could be number of colors, it could be, basically it's the size of the matrix, and then you take the limit, you're supposed to recover the S matrix. But I would say all of these tests are, so these two limits are very subtle, and if you want to really establish that something like this S matrix exists non-perturbatively, it's very hard, and I think we are very far from achieving this using any of these tools. So again, just to iterate that maybe it's a good place for the S matrix bootstrap to contribute. So that's a basic picture. And again, there's another. So the title of this lectures, it was a review paper by Giddings and Porto. And one of the conclusions of this paper is that we have found no evidence for a lack of harmony between gravity and the basic S matrix properties. And that's what I will try to see and explore, if this holds or not, and what is this harmony or not. Is it clear? Okay. So let's start, therefore, with my assumptions. I will take the basic object will be 2 to 2 scattering in D equal 4, and the important maybe the very important fact of this process in d larger or equals than 4 is that the scattering amplitude depends on two variables. This is important because I will be using it quite a lot, and then you can choose these two variables as you like, and one of these variables will be always energy, so I will call it S, Mandelstam S. But the way you choose the second variable is a little bit up to you. And depending on this choice, the physical picture will change slightly. Well, of course, you can transition between various regimes, but basically we can discuss three choices. One is that you have a function as a function of the scattering energy and transferred momentum. So T is negative, and it's related to the transfer between in the scattering process. Second, we can talk about amplitude as a function of energy and angle. Well, I can put some tilde, but let me not do it, where this T is related to the scattering angle like this. So you see that here T is fixed in the high energy limit. So if I take a high energy limit of this object, this is so-called the Regge limit. On the other hand, if I take, say, the high energy limit at fixed angles, T also goes to infinity. And finally, there is this third object, which is scattering in the impact parameter space. And this is effectively the same as, or related, closely related to thinking about partial waves. So it's the same as fixing angular momentum. So let's say you have a pair of particles in your scattering process, and they come with some energy, and they're separated in transverse plane by some distance b. Then if you compute simply using classical formula the angular momentum of this configuration, the angular momentum to leading order is simply square root SB over 2. And therefore, if you now take high energy limit of this object, it's the same as taking the high energy limit of partial waves with spin, which scales with S in a certain way. Of course, then you would like to, especially for Bootstrap, to discuss just finite spin, low spin, and I will try to come back to that. But it turns out that for gravity, this thinking in terms of the impact parameter space is rather natural. And then after we understand the physical picture in the impact parameter space, we can go and discuss the Regge limit or fixed angle, etc. But here I will find that this is the most convenient thing, and in general you should always or keep in mind in which space you're working and what is the physical picture behind. Okay, let me now explain or come back to some basic quantities that we have in gravity, and which will first of all, I will set C equal h bar equals 1, and I will, just to remind some of you, if you do not think about gravity, that we have, say, Newton's constant, and it will be related to Planck mass as follows. Or it's the same as Planck length. It was a d minus 2, and this is on my very first slide when I was talking about scattering in large dimension. This L was exactly the Planck length defined here. Now, second thing is that if you have a total energy, and let's say you form a you form a black hole out of the total energy. The black hole will have a Schwarzschild radius, and the Schwarzschild radius is given by the following formula: Rs d minus 3 equal 16 pi g Newton square root s divided by whatever, so d minus 2 and volume of the unit sphere. So the important point here, because again, I will be considering high energies, and we will slowly try to fill the physical picture. But here it's important for you to see that the d minus third power of R Schwarzschild grows like square root s. That's the basic scaling. And then, as you probably know, we expect that if you take a scattering at high energies and you confine your particles to the impact parameter less than Schwarzschild radius, then the gravity is strong. Now, in particular, there is this classic collapse criteria that you form a trapped surface and you form a black hole. Of course, in reality, when you do that, the process is more complicated. You emit gravity waves, but still the trapped surface is formed. And the first thing you expect, and even though we don't know anything about EV completion, but we will be just learning from gravity and its semi-classical limit, immediately we know that if we take B less or equal than Rs at high energies, the gravity will be strong. And so this is a regime which will be hard possibly to describe in detail, but we will try, and we'll come back to that. Now, finally, let me quote another quantity which appears in this context, and this is a black hole. So if you take a black hole with this Schwarzschild radius, and you take its entropy, so the black hole entropy is area over 4 g Newton. And if you plug the formulas from the previous picture, you get this. So it's energy times Schwarzschild radius, and at high energies, this scales like a square root s, 1 plus 1 over d minus 3. So this is another quantity to keep in mind. Now, finally, if you have a scattering of particles, we are not doing classical GR. We are doing quantum particles, so they characterized by some Compton wavelength. And therefore, to make sense of this impact parameter picture, we will take that the impact parameter is much larger than the Compton wavelength, or in other words, say SB square larger than 1. Okay. So far, I just tried to remind you that if we formulate the problem of computing 2-to-2 scattering amplitude, we have these different regimes at high energies where no matter what's your QFT at low energies, gravity will become, or we expect it become the leading force. And then no matter again what your effective field theory is, we expect the general feature of this theories is that gravity will become strong, or scattering will become strongly inelastic at small impact parameters at high energies. Now let's do something simpler and try to build up. So the first thing, what do we know? What do we know about this object, about this amplitude which we want to understand non-perturbatively? Well, the simplest thing that we know is that it has a massless pole, and in other words, we expect that if we take the scattering amplitude and we take t goes to 0 limit, there is a non-perturbative fact, which is this, plus dot dot dot, which are subleading. when t goes to 0 at S fixed. And this is, of course, probably the most familiar feature of gravity is that at large distances there is a pull. At the level of scattering amplitudes, this is the expression of this fact, but not quite. This is more subtle than that. Why? First of all, this fact is not true in 4 dimensions. It's a famous result by 't Hooft that, in fact, say in d equal 4, there is no pole, but you have an extra cut, which goes all the way to 0. And this is related to the fact that the multi-particle states are not a good description of scattering in 4 dimensions. So it's not just the fact that the planets have the Newton's potential, but it requires also something more. And the reason is this might be a bit confusing, and is the following: that let's avoid this case d equal 4. We can discuss. There is no pole, but let's say in d larger than 4, we expect that S matrix exists. We have multi-particle states, and this one graviton state is well defined. It's isolated. Then you might be confused by the following fact. I'm telling you, well, that's gravity, which becomes strongly coupled at high energies, but still, no matter how huge is S in this formula, it can be much, much larger than M Planck. This is a still correct result, and everything else should be subleading. And well, it's of course trivial because I keep S as fixed and t goes to 0, so this thing blows up. But maybe a more refined version of this is the following: that in fact, when we start doing perturbation theory and we look at the corrections to this tree-level result, we find that the dimensionless parameters that you can build is the following. You do one loop computation, you get 1 max power of g Newton. Again, on general grounds, you get 1 power of S. And then you have to you need something to make it dimensionless. And what comes out is that, well, you have the second variable, and you put it to the power d minus 4 over 2. And then this is your dimensionless parameter. And then if you have a perturbation theory where you have some 1 plus O of lambda, when lambda goes to 0, we recover this pole. Now, what is the physical meaning of this pole? Let me now do a simple computation, which is that if you want to go to the impact parameter space.
Sorry, this is elementary, but can you repeat why that is the perturbative
Sure.
parameter?
Say again?
Can you repeat why lambda is a perturbative expansion parameter?
So far, let me just say it's based on the computation. It's a dimensionless parameter, and if we will do the computation, we will find that this is a dimensional parameter which controls a correction to this formula. So I guess you could have said that, well, if I have some other mass or string scales in this formula, you can plug them in. But because this limit is controlled by IR physics, it turns out that the relevant corrections which we will care about are controlled by that. So I do not have some general argument. Yeah.
Can you repeat it? It's expanding this parameter between 1 fixed?
I'm just saying, here is that if I take the S to be very, very large, and I take t to 0, we get the pole. This is a trivial fact. And then the way it comes out in the perturbation theory is that if we will start computing the corrections will be controlled by this dimensionless parameter. So, and then when we, no matter, it will, in particular, you see that the validity, you can ask, what is the validity of the formula as the energy growth? And the point is that this formula will be valid when lambda goes to 0. And so when lambda goes to 0, it means that at higher energies, this 1 over t pole will control smaller and smaller region of t. But so far, I guess I just constructed this dimensionless ratio, so it's meaningful to discuss it. It's larger than 1 or less than 1. And we will see that indeed this pole in gravity, we expect it to control the amplitude when lambda goes to 0.
I just wanted to make sure that I'm not missing something elementary. So of course, you can multiply this by any other function of S over T. So the fact that this is the relevant parameter is something that you will explain later.
It comes from the following. Let's say we consider the leading correction. Then we get 1 power of g Newton. Let's say we go to one loop. We get 1 power of g Newton, and then based on general arguments, if you have a radial limit of an amplitude, at high energies you get 1 extra power of S. And then as you go to t to 0, you have to make it dimensionless. And indeed, so this is kind of fixed by just perturbation theory regia, and this is what makes it dimensionless. And indeed, this is what happens. Now yes, and the last comment, of course, you see that in d equal 4 you lose this sort of decoupling, and indeed you lose the pole, you're left with a cut. Now it is very physical if you do this compute scattering amplitude in impact parameter space, and it's defined by doing the Fourier transform with respect to transferred momentum. So here, what I did is that we consider the scattering in so-called bright frame, where the particle only in the scattering process changes the transverse momentum. This is the exchange momentum Q. So this is a bright frame. And then you do the Fourier transform with respect to this Q. And what you get is gamma d minus 4 over 2 g Newton S. And here you get pi d minus 4 over 2. Sorry. And b d minus 4. So indeed, what happens is that here, when you do this Fourier transform, the t is of order 1 over b squared. And therefore, what we say, when we say that here the pole controls this small t behavior, it's the same to say that at large impact parameters, at any arbitrarily large distance, energies, interactions become weak, and then the leading interaction is just given by a tree level. So it's some form of, if you wish, a gravitational clustering where no matter how big is the energy, at high enough distances, interaction goes down. But here we just see it very explicitly, and you can rewrite this formula like this. Let me do that. Square root S B and RS B d minus 3. So this is just using the scaling I wrote in the previous formulas. And just to step to the next move away from this very simple regime, let me notice that I told you that this parameter should be very big, which is that the impact parameter is much larger than the Compton length. And this parameter is, if we want to stay in the controlled regime, we want it to be small. And because the phase, this amplitude is given by a product of the two, you see that you can imagine a regime where this parameter is very big, this parameter is very small, and the whole interaction can be either big or small, depending on which parameter is bigger. So in principle, now that if we understood this simple regime at very large impact parameters, when this amplitude is very small, it goes to 0 at large B, we can try to see, can we extend this range while still keeping control? And the answer is yes, so let's do that. But before that, let me start drawing the picture, which will be improving. Oh, it doesn't have this feature. Right. So we plot here log S. We plot here log B. So let me chop the region S, say, this is SB square equal to, say, order 1. So we do not go there to talk about impact parameters. Here we will talk about spin. And so far what I told you is that if we look at this plane, there are 2 lines, which is at which is the following lines. Imagine that we look when this phase shift is very small. It means that the tree-level interaction is very weak. So let's see which region in the B plane it covers. And we see that this formula, being, say, some fixed but very small parameter, scales as s to the power 1 over d minus 4. So therefore, we see that in this plane, we have this line, 1d minus 4 log s. And here, we have this line, which is 1 over 2 d minus 3 log s. This line comes from impact parameter being equal to the Schwarzschild radius. So this is just b equal to rs. And so far what I told you is that we expect that here gravity is weak and elastic, and here gravity is strong and inelastic. Okay, this is a collapse region. This is this region where things factor. Now, can we go inside here and say more? There is this very interesting regime, which is a regime where we keep this guy small, so we keep the impact parameter to be big, but we start making this interaction to be very large. And you see that as this guy becomes large, it looks like, well, perturbation theory breaks down. We need to resum something. And so this is an interesting regime. And this is a regime which is described by iconal scattering. And here we want to extend the previous picture to the regime where this tree-level phase shift could be much larger than 1. So what happens to the amplitude in this regime? The proposal is that, let me write first the answer, and then we will discuss it. The proposal is that in this regime, the amplitude becomes the same as on the previous slide, but we simply exponentiate this tree-level phase shift in the impact parameter space. And let me define, sorry for my definitions, but I define twice delta tree as being this T of S and B tree computed on the previous slide. So what happens here is that if we take the impact parameter to be very large, then the phase shift is very small, and then we can expand it, and we're just back to the previous formula, where this becomes of order simply delta 3 when it's much small. However, now the proposal is that when this guy becomes very big, so when the phase shift acquired in the scatter becomes bigger, we still can write a formula, and the formula looks like this. We simply take this phase shift and exponentiate it in the impact parameter space. Why such a formula makes sense or could be true, or when is it true? That's a question. So one way to derive this formula, people sometimes you see, you go through the resummation of certain ladder diagrams, but maybe a little bit cleaner way is that, again, general relativity comes to the rescue in the sense that if we look, we see that this regime is described by semi-classical computation. The semi-classical computation is it's a propagation of a particle through the Exelberg-Sexel shockwave background. So the idea is that this formula describes propagation through the shockwave. What is this shockwave? So if you take a particle with a stress tensor being, so now this is a classical background of this type. So it's localized on a light cone and in a transverse space, and you plug it into the GR equations of motion, and in fact you can plug it into any high derivative theory. The result does not depend on it. It's an exact solution anyways. So what you find is that this particle, or this stress tensor, better said, develops a gravitational field, which is basically this tree-level phase shift that we encountered on the previous slide. So it's energy times G Newton times this thing. And here you have this corrections, and then of course you have the transverse space undeformed. And here, what is this B I defined as simply B is defined in this case as a transverse separation. And so now, let's say you have an energetic particle, it sources a gravitational field, and what you do is that you consider a propagation of a probe particle on this field. Let's say the shock wave is sourced somewhere here. So this would be, this would be x minus, x minus equal to 0, and this is x plus. And now you send an extra particle through the shock wave, and let's say what happens is this experience this kick. This is the x plus x minus, and in the transverse plane it looks like you have a source at the origin, and the particle, the probe particle, say, let me call it the cross, propagates at impact parameter b. So this is a probe. This is a source, and this is the effect. So therefore, we can now consider a propagation of a particle on this shockwave background by doing simply the classical equation of motion. And what you see is that when you cross a shock, wave, you acquire a simple kick of the wave function. So P plus is the momentum of this guy. This guy carries momentum P minus. And so the effect of the propagation through the shock so this is the shock wave, is exactly this phase. And this is precisely the phase which appears here. So therefore, this formula, it exactly describes the propagation through the shock wave. And you expect that it will be valid only when this picture is correct. And we know that this picture, well, it has several limitations. One is the relativistic particles are not really localized as delta functions. Second, you can have, if your impact parameter, say, becomes of order of some object you have in the theory, for example, a string, this will get a correction. So you can have also, start maybe emitting gravity waves. So there are corrections to this formula. And we would like to understand how do they behave and when do we can trust this formula. So let me focus, as I always do in these lectures, on high energy behavior of the amplitude. And let me ask, so here's the formula written, what is the behavior of this formula in the radial limit? So what happens if we keep, now there is a switch. Here there was impact parameters fixed, and here I now want to compute it in a fixed momentum transfer, so T iconal S and T. So let's just, and to do that we simply now perform this integral with this phase. This is what we want to do. And to do that, it's convenient to rewrite the integral. Maybe let me not spend time on this simple rewriting, but point out that if you do this Fourier transform, you get a saddle, and this is a sort of very famous saddle. It is, let me call it, well, I don't know if it's correct to call it like that, but let me call it the ACV saddle. And ACV here stands for Amati, Cefaloni, and Veneziano, who studied in detail these processes at the end of the 80s, beginning of the 90s. And the interesting thing about this ACV saddle that you get is that it's located as follows. You have square root minus t. So this is a momentum we keep fixed. And here we have g Newton s divided by b star to the d minus 3. So this is what you get if you simply take this Fourier transform and you compute the saddle in the b space. You'll get that the saddle is located at this location. Now, why is that good news potentially for us? Is that, let me remind you that the R Schwarzschild was scaling like s to the power d minus 3 over 2 at high energies, but this ACV saddle, b star, scales as, oh, sorry, this is wrong. It was 1 over 2 d minus 3 Whereas the ACV saddle, it has a behavior s to the 1 over d minus 3. Therefore, we see that at high energies, B star is much larger than Rs. In other words, we expect that the gravity is still weak. And we can, in fact, at least trust this computation, because it's really an IR computation. That's the basic point. That what we learned from this formula is that if we take this iconal representation of the amplitude, and we take the Regge limit with t fixed and s to be large, it's controlled by the IR physics. It is much simpler than QCD. Gravity is much simpler than QCD in the Regge limit. Now, in fact, you can compute the value of the saddle exactly. And it has the following features. Let me not write the numbers, the numerical factors, but it has s square root minus t to the 2 minus d over 2. And then it has these parameters that we discussed already. G Newton, s minus t d minus 4 over 2. This is a dimensionless parameter. To the power d minus 2 over 2 d minus 3. And finally, it has a phase. And the phase is, again, this dimensionless parameters that I wrote. To this power. Okay. The interesting thing here that you get is that this is when s goes to infinity. The interesting thing that we get here is that we get, well, apart from a highly oscillating phase, we get a power, and this power T is fixed. T is fixed. T is negative and fixed. No, in fact, yeah. So there is this minus 1. I guess that's what you mean. So yeah, there are these two terms, but the claim is that this saddle point correctly captures exactly this combination. So this minus 1 is effectively cancelled by large impact parameter physics, and so this integral is dominated. So the sum of these two terms is controlled by this. The result of this Fourier integral is controlled by this saddle. And
question.
Oh, it's yeah. I can give more details. Yes.
So also have a question. So B star in this game, it's a transfer scale, and you're saying that it stays well separated. Well, how about the short longitudinal scales?
Very good. Thanks, Slava, for the question. We will come to that next. Yes, that's an important point. We will come to that next. Okay.
Okay.
Yeah.
On a couple of slides ago, you had a specific definition of B. I was wondering, like maybe before that, the picture, even before this, the definition of the impact parameter, actually.
So this is a transverse Q, and the B was defined by the Fourier transform. More effectively, this is, if these are the trajectories, this is B in coordinate space. So this is Fourier.
Right. So I guess there'll be some. If you only look at the incoming particle, there'll be a naive kind of B, which differs from this by cosine of angle.
Exactly. Yes.
The probe analysis of in the shockwave background doesn't know that, right?
Yeah. So exactly. So in the literature, I guess in the gravity wave literature, there are these two B's, as she was pointing out. So one B was the picture was, I guess, somewhere here. This one, so you have a really imagine the naive B. And this is the B which is related to the large J limit of partial waves. So it is sometimes called Bj. And then there is this B which is related to scattering in the bright frame. And they related, which is related corresponding to this picture. And then they are related through cosine, which okay, so the point is that at high energies, for me, it will be not important because the correction will be subleading. But if you want to compute corrections, it is important, and one should keep in mind this relationship when going from, so let's see, what's happening? So there is this relationship Bj. Okay. I guess it's loading. Okay. So yes, there is this cosine. If you want to do one loop and two loop and compare, it is important. But at high energies, the difference between the angle goes to 0 is small. So it does not play any role. But in principle, yes, one should pay attention to this, and people do that in the computations. Now, second, before we go on. Okay. I guess it needs a restart.
Can you give the relation between Q and this Q momentum and T?
Yeah. So T is equal to minus Q squared. That's a relation between the two. Okay. I'll continue here. And let me just notice also that if you take the d equal 4 limit of the formulas that I wrote, it's a finite limit, and you get well, almost finite up to an overall phase, but you get g Newton square over t times this phase, which I already wrote. Can I continue here? Okay. So this is the result in 4 dimensions. Now, as Slava pointed out, yes, and one final comment, which is that we saw that when at large energies, when this parameter lambda, which was defined as g Newton s t 4 minus d over 2 goes to 0, this was d minus 4 over 2. When it went to 0, we had a pole, but on the iconal saddle, lambda goes to infinity. So it's really a different regime, but miraculously in GR, both are controlled by semi-classical computation. And so, well, this is just the tree-level computation, but this is a semi-classical computation. And if you compute the behavior of the amplitude on the saddle, you get s to the power 2 minus d minus 4 over 2 d minus 3. So it's strictly less than 2 in d larger than 4. It becomes exactly 2 in d equal 4. But also notice that there is this very strongly oscillating phase in S. So if you smear a little bit in S, you expect that the amplitude will be damped much stronger. Now we have to worry, as Slava pointed out, that there was this delta functions. We have to worry about the longitudinal spread. And in particular, we would like to make sure that on this iconal saddle, if we compute the curvature invariant, it should be much less than the Planck length to the fourth. Now, what happens is that let's do this computation. So let's move L Planck here. The Riemann tensor here, it's for the shock wave, it's something like U ij u in a transverse where ij goes in transverse plane, and it's given by effectively a second derivative in B of the phase shift. And then there was this delta U and delta V, and this should become some relativistic spread of the wave packet. So for the pair of shocks, we write delta U and delta here, delta U and sorry. So let me explain a bit. So the curvature was localized on delta U for the one shock wave. If you now take a second guy and look at the scattering of two shock waves, it seems like you get so the second one will be VV ij. So if you take a product of these guys, you will get this square, and then you will get naively something like delta U times delta V. But of course, we need to take effectively, this was just the width of this relativistic wave packet. So what we need to take 1 over delta U delta V. And if we imagine that these amplitudes that we are discussing, they correspond to one maximally sharp wave particles in the momentum space, then this delta U and delta V, they are simply of order 1 over energy. And so this 1 over delta U delta V produces a factor of S. And so we want that this guy is less than 1. So this is the condition. And you can rewrite this condition as, well, whatever, delta 3 to the d over 2, so s d square less than 1. And in particular, this implies that B should be much larger than Schwarzschild radius, which we already knew. But this condition is completely fine on this iconal computation. Now that suggests that we have to add a new scale to our, and this spread, as was pointed out and worked out 20 years ago by Slava and then Slava's paper with Steve Giddings, it will become important when we talk about collapse. But I will talk about it later. Here we don't care about collapse. For this iconal computation, this is fine. So now let me draw the picture again. We have log S, we have log B, and we have already, unfortunately, I guess I lost the previous copy, so let me draw it again. So this as B squared. Now we had this line this line was 1 over d minus 4 log s. This was just tree level, where the tree level phase shift should be fine, so gravity is weak here. Then we had this line, which is 1 over 2 d minus 3 log s. This was strong, tentatively. And, but now we have a new line, which we add to this picture. And this new line is located here, let's say. And this is a line 1 d minus 3 log s. This is the line of the iconal saddle. So this is precisely what we got here. Well, I don't have this expression for the iconal saddle. Let me write it again. It was square root minus t, which is the same as q, was equal to g Newton s b to the d minus 3. So if you want to keep q fixed, say, and you take energy to be large, then you see that b scales like s to the power 1 over d minus 3. So this is this picture. And yes, we will now be crossing this line. Yeah, here is iconal approximation is good. So now we want to understand when it's bad. And here the scattering, okay, it's maybe it's not weak. You have to do this shockwave computation, but it's purely elastic. In other words, all the SJs go to 1. So let me not go over it. So next, we need to discuss what are the further corrections. What are the further corrections to this picture? So there is a few, and this depends on the physics of the objects. In particular, I think the important question is, as we scatter things, the sizes of the object effectively grow with energy. So in QFT, we know that objects do not grow faster than log s, so it's a Froissart bound. In tree-level strings also spread like log s, but we can imagine there are some exotic objects that maybe spread very fast with energy, and so maybe then they somehow spoil this computation. So to me, it seems like the validity of this computation, it's a dynamical question about the nature of the physical objects in the theory and how does this object grow with energy. So let me discuss a few effects. The first effect is the following. Imagine that you have in your theory some degrees of freedom in which your particles can be excited. So then you expect then when this invariant, the curvature invariant in the scattering region, becomes of order of this, it's called sometimes diffractive scale, then you will start excite just the tidal forces as your object pass through each other. The tidal forces become strong enough to excite them. For example, if you do proton-proton scattering, m star will be lambda QCD. So then you will have some hadronic excitations for PP. And if you scatter strings, it will be string scale for strings. This is a very simple expectation.
I'm sorry, but there's always gravitons. If you pursue this line of thought, you could say, well, there's always going to be some gravitons excited. They are massless.
There would be gravitons excited. That's our next point.
But then m star is equal to 0.
This is different, though. So there is here I'm talking about do not change the number of particles, but internally excite your thing. Let's say you send the hydrogen. The hydrogen will be excited, but they do not produce hydrogens. Gravitons we cannot excite, but we can produce them. So I'm talking here about the excitations of things. So this is the estimate, and if you plug if you plug our previous calculation, you'll find that the relevant phase shift, you expect the tidal excitation when this guy, delta tidal, let me define it, was purely imaginary, become significant. And again, if you want to do this computation microscopically, well, one can do it with a hydrogen, or one can do it with strings. You will get this result. With hadrons, I guess it's more complicated. So therefore, we see that, what does it mean? That here, as our particles pass through each other, they can change their identities. They can get excited into something else, x and y. And therefore, the amplitude develops the imaginary part. And therefore, the iconal computation should be breaking down. But now let's look how this guy behaves at high energies. And we see that at high energies, it grows like this, 1 over d minus 2 log s. Therefore, you see that if you sit on the iconal saddle, as you go to high energies, the tidal effects are irrelevant. Second effect we need to discuss is a universal effect, which is a production of gravity waves. Because we can always produce gravity waves. And here, again, this is this ACV computations. The first diagram you can compute is like this. And here, the result is that you get the characteristic phase shift. And again, when I say characteristic phase shift, I mean the following. We compute the effect of this diagram. It is given by this formula. Gn cube s square b to the 3d minus 10. So when it becomes significant, you start producing gravity waves. This is the result of evaluation of just this diagram, where you can think of this. This is a graviton. So if you cut, you're emitting graviton. So it's a two-loop computation. Then, of course, we need to think when is this computation valid, and et cetera, et cetera. But let me just go with it for now. And therefore, so this is tidal. Finally, we have gravity waves. And here it's over 3d minus 10 log s. Let me see. It should be, I guess, one half. So it should be twice here. So again, what do I mean by this picture? Is that we estimate the tidal and gravitational wave effect, and we want to see when they become significant, and we see that they become significant at higher. If you take the energy to be large, they become significant at higher and higher impact parameters, as you expect. Now, I want to make, how much time do I have? Okay, perfect. I want to make another comment, and a few comments, and then finish. So the first comment is the following. So we have to, if I want to trust this computation of this gravity wave based on this analysis, in principle, I need to evaluate this invariant at the relevant impact parameters and check that it's much smaller than the Planck length. And this is, I guess, what was pointed out by Slava 20 years ago, is that if you do the estimate of this Kreichmann scalar curvature invariant on a gravity wave and on a collapse region, you find that it becomes a 401. In other words, it looks like this wave packet estimates that we did, instead of getting something that's much smaller, we get something which is big. So there is a small asterisk for gravity waves. For gravity waves, it only happens for d larger than 6. So if in d equal 5 and 6, it's still small. For collapse region, for this estimate, it's always big. And so then you might think, okay, well, we make some argument based on the trapped surface, but the curvature is Planckian. To what extent we can trust this calculation? And well, the idea was, okay, let's change then the support of the wave packets, and we can consider this by smearing the amplitude in S, and by doing that, we expect that this is the same as considering the wave packets of finite longitudinal widths, and then you can check that the region in the curvature in the collision of the shock waves is given by L Planck to the 4. It's the same computation as before, but now the curvature square times the wave packet length. And so this should be much less than 1 if you want to trust your classical analysis. And what was pointed out by Slava and Steve Giddings in the past is that if you can easily choose this delta S such that in the collapse region you can get this condition. And similarly, you can choose this delta S such that the condition is satisfied in the gravity wave region. So my reading of these statements is the following, is that when we look at this picture, first of all, I ordered the lines according to d larger than 6. You can check that when d becomes 5, these two lines change. Gravity waves kicks in first, and tidal. But so the important thing is that it seems like here, and this is the first point where it would be nice to have some non-perturbative bootstrap-like insight, which I will be coming again into this picture, is that it seems like from the classical gravity computations, for these two curves, especially for the collapse curve, it is important to do this smearing in S. And I don't think we know from any independent computation the role of this smearing for gravitational amplitudes at high energies, smearing in S. Now, there is a second interesting point. Notice that here, when I'm writing these formulas, I put the phase, again, this formulas get erased, but let me write it again. When I write the formula of this type, the G Newton is already in the exponent. So G Newton is already in the exponent. So we already resummed G Newton. And the conjecture, which we can call the ACV conjecture, is that effectively this is, as we decrease impact parameter, this formula is still correct. You need to change the phase shift, but all corrections organize as you expect them to. They organize as corrections in the string scale, so you can have corrections. You can have corrections of the type, say, lambda string square over b square, which will correspond to tidal excitations, and you can have corrections R Schwarzschild over b to some, well, and usually the power to the power d minus 3. But that otherwise this is the right picture. We see we can describe the scattering with this phase shift operator with these corrections. Now, there is an interesting subtlety. If you compute this diagram and you try to read off the phase shift from this, this computation, according, as I just told you, we expect it to organize some delta tree. This is a leading saddle answer, and then this is a correction, our Schwarzschild, to the b to the power 2d minus 3. So as expected, this is a correction that we wanted to get, or we expected to get. The subtle fact about this computation is there is an extra log s here. And then it seems like this log s would violate this conjecture which I told you, where everything is given by delta tree plus corrections which are organized by the scale, because now this just blows up with energy. This is related to something called energy crisis, I guess in the gravity waves, people computing the total energy of the emitted gravity waves. And again, here the conjecture is that if you do a double resummation or at some finite G-Newton computations, and there are some proposals how to do it, this log s should become, again, some log Rs over B. So this is the conjecture. So this is to say that, say, understanding this log s and doing this computation and going from this H diagram to putting this guy in the exponent and making sure that we control it at large log s, it's a tricky business, especially for these gravity waves. The tidal guys are under control. And as we go to the collapse region, we lose control, and then maybe this classical picture requires some smearing. Maybe it's still fine. I would say we do not really know, but I think that this is a physical picture. Now, if you believe this physical picture, if you think that it's correct, then you see the following things, that as we take the radial limit is controlled by this saddle. So this is the radial limit. And as you go to high energies, all the effects, and you can also consider Kaluza-Klein modes, and they also do not change the picture. You see that as you take energy to be large, all these other effects, they become irrelevant. And so this suggests the following statement, that we have that if we take the scattering amplitude in gravity, and we take a radial limit, and we take and divide it by result on the diagonal saddle, that this goes to 1. So we can, well, I guess we can call it quantum Regge growth conjecture. Like similar, that the statement is that if we take a quantum, if we take 2-to-2 amplitude in any theory, the physical picture suggests that we know the radial limit of this amplitude along the real axis. It's controlled by the diagonal saddle. And again, according to, coming back to the Slava's point on this ACV saddle, it goes to 0 at high energies. Or in other words, Regge limit is IR. It's controlled by IR physics. Now, let me comment on what, well, maybe I will not comment on the on fixed angle, because you can ask, okay, what does it imply for fixed angles? Maybe we can discuss this later. But let me just say that at this point, we arrived at a, well, we almost arrived at the interesting set of statements, which is that, let's say, as the starting point for these lectures, you believe into the fact that the amplitudes obey these basic properties of analyticity, crossing, and unitarity. Then we draw some S-plane. And basically, and if you assume now that here you get that the t is less than s squared, this is what we just derived using this iconal. You can do a much more refined analysis with less assumptions, more assumptions, but that's a basic punchline. So this is unitarity, if you wish. So then if you use crossing, you use it's less than s squared here. And then if you assume that the amplitude is sub-exponential in the upper half plane, by sub-exponentiality I mean that t here is less than e to the s beta, where beta is less than 1. So again, this is an assumption. I don't know how to prove it. So this picture suggests that we have going to 0, and therefore we have a twice subtracted dispersion relations. And this is something that people have been using recently a lot to so here, to derive various consequences. But next, I guess I will then start with trying to see. I show you this picture. I show you this picture. Here there was the amplitude was controlled by tree level. There was a pole. This was controlling the Regge limit. Is this picture consistent with a twice subtracted dispersion relation? Because it's not obvious a priori if it is. And so next I will start checking the basic property of this picture within the twice subtracted dispersion relation. I guess I'll stop here. I think so.
Okay, yes.
So, in the context of string scattering, where does Gross-Mendel saddle fit in this picture?
Yeah, very good question. I was planning to go into the stringy regimes next. So the picture is that here there is an important point which you mentioned in your lecture, which is R Schwarzschild is equal to L string. So this is, I guess, this correspondence point. And here there is a scale of L string, so we expect that here there is some stringy physics. And then there is the following thing happens. So for Gross-Mendel, the prediction, well, there is a Gross-Mendel saddle, which is okay. There is a Gross-Mendel saddle, which is of course obvious, but for the tree level. But I assume you ask me about the resummation, this Borel resummed, yeah. So of course, if you sit at low energies, it's tree level string. You have Gross-Mendel at fixed angles. But the interesting also question is that they have this proposal that if you Borel resum the amplitudes, you have the square root s. Times a function of an angle, and I will maybe discuss it just later when I discuss strings. You will see that when you start with ACV, the ACV picture is that at very small angles the Gross-Mendel saddle is subleading, but as you increase angle and you keep energy not too large, there is a region which looks very similar as Gross-Mendel. You get square root s times some dependence of the angle. So I guess it's energies which are not too large, and I will review not too large, and the angles not too small. That's where you're supposed to match to this Gross-Mendel saddle according to ACV. So that's, I think, at least this is their picture, and the square root log s comes out, but it's a bit interesting. Well, I will talk about it next, I guess.
Okay, more questions?
The difference between the tidal and gravity wave lines? in 6 dimensions where they coincide?
Okay, I could have done some mistakes in my things, but if they coincide with the proper numbers, which I should check, I don't think they coincide in 6 dimensions, but here I would say that because the argument is so crude that the details will be probably different. For example, you see the important thing here for the tidal, that there is this new scale that enters, which is absent for the other one, which is controlled by just the Planck scale here. So if you have something much lighter, I guess you will you could see this scale, but otherwise probably we have to look at the subleading structures, subleading corrections, so this kind of more refined structure. But again, it seems I have to be a bit more precise, because as you saw, the amplitude also has a very intricate phase on the iconal. So I think we expect that in this region the amplitudes also they're highly oscillating, and sometimes, for example, this tidal line in string theory is under relatively good control, as we will discuss next. But the gravity wave line is, my impression, is never under good control. So it's really would be interesting to see what can be said about that.
So you said it obeys a twice subtracted dispersion relation, but I think, so why is there no D dependence? It's just, you said the S squared, that's just a bit of a crude analysis.
Yes, so I think well, at least what I will try to test next time is that if you take this formula, which again is not here, but...
This one maybe.
This?
Yeah, is that what?
Yeah, so in principle, I can remove the absolute value. I can write the precise formula with all the T dependence. And I will be testing that one. So this twice subtracted dispersion relation is a crude, it's a simple thing which seems to be very useful. So, but otherwise it seems like there is a more refined.
And it doesn't get better than twice subtracted because...
Yeah, because this is bounded by... by 1, and if you want, I think if you want to go to ones, if you want to improve the convergence, you have to smear over the impact parameters, or maybe over S also, or either or. So one has to introduce various smearings. For example, at least I haven't done this exercise of taking the iconal amplitudes and smearing them over S, to what extent this phase damped it stronger. So we know that over impact parameters it does improve it. Yeah.
Okay, if there are no more questions, let's thank Sasha again.